Hey guys, welcome back to Food for Thought Physics, where today we're going to be doing an example problem in 1D kinematics, which reads, I am standing on a 40-meter high cliff and toss a ball straight upwards with velocity 15 meters per second. It hits the ground below the cliff. Ignoring my height, determine A, the time it takes for the ball to hit the ground, B, the velocity of the ball when it hits the ground, and C, the total distance traveled by the ball. So here we have this small diagram of this problem here. I'm going to be standing on this cliff 40 meters above some ground down here. This ball, which is in red, is going to be thrown up, and then it'll come down due to gravity and hit the ground. So, before doing anything else here, as in most physics problems, as I mentioned before, we're going to be establishing a coordinate plane first. So this coordinate axis, this coordinate axis is going to be in the vertical direction, because the 1D motion of this ball is going to be vertical. So I'm going to set this upwards direction as positive, and this ground position down here as 0. And so that means that the initial position of the ball here is going to be x naught equals plus 40 meters above the ground. And the reason I'm saying this is 40, even though this ball is actually in my hand, which should be above 40 meters, is because we're ignoring my height here. We're pretending that my height here is insignificant compared to this 40 meters of the cliff. So we're just going to approximate the ball's original position as being 40 meters for simplicity. So now we have our x naught, which is plus 40 meters. And what else do we know? Well, we know that the ball starts off by coming upwards with velocity 15 meters per second. So I'm also going to write that down here. I'm going to write v naught equals plus 15 meters per second. And this is because our initial velocity is going to be 15 meters per second the moment I throw it up. Right, so what else? Well, what makes the ball come down, you might ask? Well, this is because of gravity, and in case you didn't know already, an interesting property of gravity is that it's going to be constant acceleration. So gravity causes constant acceleration, at least near the Earth's surface. And the reason for this we're going to be looking at in a future video, but for now, all you need to know is that for any object near the Earth's surface, gravity is going to act on the object with a constant acceleration, which we're going to call g. And this constant g here is going to be approximately 9.8 meters per second squared. So this meters per second squared is going to be a unit of acceleration. It can also be written as meters per second, which is just a change in velocity per second, because meters per second is a velocity, and this velocity is going to be changing per second. So g equals 9.8 meters per second squared. Any object sufficiently close to the Earth's surface is going to be acted on by the Earth's gravity with this acceleration. And of course there are other things that might come into play like air resistance and friction, but we're going to ignore those for now for simplicity. So we can just assume that this thing is going to have an acceleration of negative, actually, 9.8 meters per second squared. And we put this negative here because gravity is always going to be acting towards the ground. And we set upwards as our positive direction, so gravity is going to be acting downwards, or in the negative direction. And now we know that this is a constant acceleration problem, we can start thinking about our acceleration equations. So let's start with these questions here. So part A asks the time it takes for the ball to hit the ground. Well, what relates these variables here to the time of anything? Well, first thing I can think of is the position function, which, remember, for constant acceleration is x equals 1/2 at squared plus v naught t plus x naught. So what we can do is we can plug these things into here, and actually this x over here, x is going to be 0 because we want the time it takes for this ball to start from this x naught, and based on these velocities and accelerations, it's going to come down and hit this ground here at x equals 0. So we can rewrite this as 0 equals 1/2 times negative 9.8 t squared, and I'm going to be ignoring the units here because we see these units are all in meters and seconds, so they're all going to match up automatically. So we're going to not write the units here, although formally you should actually write negative 9.8 meters per second squared and so on. But we're going to say 0 equals 1/2 times negative 9.8 t squared plus 15t plus 40. And now we have this quadratic equation in t. So we can solve this with the quadratic formula, which I assume you all know. I'm not going to write it out in detail here, but using the quadratic formula, we can solve this equation here, and we can get that t equals about 4.77 seconds. So it'll take about 4.77 seconds for the ball to fly up, come down, and hit the ground. Alright, now let's look at part B. Part B is the velocity of the ball when it hits the ground. And well, we know that the velocity in constant acceleration is going to equal at plus v naught. So since we already know this t here, we can just plug this t in here, and we're going to say that the velocity is equal to negative 9.8 times this 4.77. Again, we're ignoring units because everything is in meters and seconds here. So negative 9.8 times 4.77 plus v naught, which is 15. And plugging this in and solving, we get that v equals around negative 31.8 meters per second. So this is our answer to our second problem here. This part B, which is the velocity when it hits the ground. So it'll hit the ground with a velocity of negative 31.8 meters per second. Now note that after it hits the ground, obviously its velocity is going to be 0, or maybe some positive number if it bounces. But right before it hits the ground, you can think of like, if it's infinitely close to the ground, but it hasn't hit the ground or bounced yet, then the velocity is going to be this negative 31.8 meters per second, or 31.8 meters per second in the negative or downwards direction. Finally, part C, the total distance traveled by the ball. Well, we might say, well, this ball's displacement, overall displacement is going to be just 40 meters, or negative 40 meters rather, because it starts from over here and ends up down here. But here we want total distance covered. So this is going to include the ball's motion upwards and downwards. Well, we know that the ball is going to come up, come back down past the original position, and then go down another 40. So if we just find this distance up here, which I'm going to draw this whatever distance up here, then we can just add 40 to that answer. So what is this distance up here, you might wonder? Well, here what we can do is we can use the no time equation. So, well, we know at the peak, the velocity is going to have to be 0, right? Because the velocity is going from a positive value going up to negative. So the velocity is going to be instantaneously 0 at that point. So we can use this equation here, which is, remember, the no time equation is going to be v squared equals v naught squared plus 2ax. And so we know v squared we're going to set is equal to 0, because at the peak it's going to be 0. The velocity is 0. So 0 squared, which is just 0, equals v naught squared, that's going to be 15 squared, or 225, plus 2 times 9.8, or times negative 9.8, times x. And solving this, we get that this x here is going to equal 11.5 meters. So that means, well, if x equals 11.5 meters, this means that the ball travels 11.5 meters upwards before stopping at the peak, and then it comes down. And you can think of it, well, if it goes 11.5 meters upwards, it must also go 11.5 meters down to get back to the original position. So we're actually going to double that value, and then we're going to add this extra 40 meters from the original position down to the ground. So our final answer is actually going to be 40 plus twice 11.5, which is going to be 63 meters.